Here, and let me share my screen with everybody. All right, so hopefully everybody that's online can see my screen right now. If you cannot, just let me know. But we'll go ahead and get going then. It's too bad that this pen's not working too. So yeah, so last time we discussed important topics. We discussed things like displacement. We discussed things like velocity. And in those cases, displacement is something that has units. It's of length, and we use meters for the unit that we discuss when we're working those problems. Velocity has units of distance over time interval, and so in this case, we might use something like meters over per second as our units that we use for um, discussing things like velocity. And one of the main points that we drove to distinguish is that um, displacement doesn't just have a magnitude, but it also has a direction. We need to know whether we're going north, east, south, west, or whether we're moving to the left or to the right. And so this introduces this idea of what we call vectors. And so, for example, we might have so there's going to be a quantity called scalars, and there's going to be a quantity called a vector. Examples of vector quantities, and this is what this slide's illustrating, is that we are going to move this out of the way. So for example, quantities like displacement fall under the category of a vector. And the corresponding quantity that's a scalar is what we call the distance. So a unit of, so something like distance doesn't tell you where you're going. Displacement has both magnitude or size and direction. And like I said, this general property of vectors, it's a general property of vectors. And a scalar is only going to have, well, magnitude. So there's another quantity that we talked about in the previous lecture, and that was velocity. And velocity is also one of those properties that has size and direction. We don't want to only know, how fast we're going, but we want to know where we're going. So the corresponding scalar in that case is speed, okay? And speed only has the size. And so when you see the cartoon here, we have a Jane that starts off at some point on the left-hand side of the intersection, and then moves on over at a new location. When you look at Jane's blue arrow, her arrow, the magnitude of the arrow, is about the same size as Sam's arrow. So Sam has a different displacement, but he moved horizontally. But in terms of the size of the arrows, you can almost imagine that if you got Jane's arrow rotated, it would fit right on top of Sam's. So that's indicating that they have the same magnitude, but the direction's different. And so we need to have a way of distinguishing that. And so it turns out that with vectors, we're going to be able to represent vectors as arrows. So the idea here, we're going to represent vectors as arrows. And there's going to be some important things about the arrows, where the size of arrow is going to give you the magnitude magnitude of the quantity. And I'm saying quantity because it's not necessarily distance. It could be like the velocity, the magnitude of the velocity. And then the direction of the arrow gives direction of the quantity. So, and we're always going to draw the arrows from where you start. That's where you put the tip of the arrow to where you end. And that's going to be, so the where it starts is the tail and where it ends is the tip. So in this little cartoon that I've drawn here, we can label this part here. So that's going to be the tip. I mean, sorry, the tail. Really wish I could use this pen right now. So, as I said, that part's the tail, and the front part is the tip. And I'm going through the effort of writing these parts because we're going to need to learn what's called the tip-to-tail method of adding vectors in a little bit here. So let's kind of look into this idea of adding vectors. So it says here, the net displacement for a trip with two legs is the sum of two displacements that make up the trip. So, you know, if the idea here is that we want to add A plus B, and we make a vector called A that looks like that, and we make a vector of B that kind of looks like this, then when we're talking about distances, it kind of makes sense that, you know, if you're going to take a trip, you're going to, you know, you count how far you went in one part of the trip, and then you add up what you did in the second part of the trip. So, however, what tip-to-tail method tells you to do is you basically take your vector. So in this case, I took vector A, and you kind of have this method of like drag and drop, like dragging the vector. So what I did in this case is I just copied vector A and I put it here on the right-hand side. So notice that in this process of dragging, it's also known as translating the image or the vector. This is kind of what you do when you click on an image, like on PowerPoint, you drag it around. We're not rotating it, we're not changing the size, we're just moving it to a different spot. And so if you want to do, if your goal is to do the sum of A plus B, so let's say we want to have as a goal to add vector A, so do the operation A plus B. One thing that first of all you'll notice is every time we write down vectors, they put a little arrow symbol over them. And I'll be doing that in class as well, except today because, you know, things aren't cooperating. But that little arrow that you see on top of the letter means that you're dealing with a vector quantity. And it's going to be important later on when we start dealing with vectors in 2 dimensions, so that you don't mess up and do the wrong kinds of operations. But the idea when you do vector addition is you're going to take vector A, and remembering the parts of these things, we have the tail. That's the tail right there. And then the tip, which is at the top here. We're going to use what we call the tip-to-tail method. All right. And so what that means is we're going to take vector B that also has its own tips and tails. And so we're going to take vector B, which I need to label a little bit better here. I don't know why it doesn't. Okay. So the idea is you take all of that, you drag it over, and what you're going to do, so this is basically tip to tail method, means you're going to write down A first, you're going to put to the tip of A, you're going to connect the tail of B. Something kind of like that, where you make them kind of touch. So the moment you do that, then the answer is going to be the new vector that connects where you started from with where you ended. So we started here on vector A, and then we finished at vector B, at the tip of vector B. And so in this case, your answer is going to be the arrow that connects your starting point with your ending point. So in this case, that's going to be, that red arrow represents the answer, so to speak, or the sum of A plus B. So, all right. So, and that's kind of what they're illustrating in that in the graphic here on the right hand side. Take A, tip to tail put B, and then A plus B is where you connect the start to where you connect the finish or the end part of the drawing, okay? So let's maybe try to do one of these examples real quick. So here it says, given vectors P and Q, what is P plus Q? So you're gonna go about it the same way, where you're gonna draw a vector P, and then you're gonna do tip to tail to attach vector Q to the end of that. So based on that, let's see what kind of an answer you can get. Of course. All right. So in this case, what we're going to do is we're going to draw vector P first. Looks like that. And then we're going to take vector Q, and it's this vector that is horizontal, and it's pointing to the left. And so if you do tip to tail method, then the idea is you're going to take P, which is here, you're going to do the tail of Q, and you're going to put it on the tip of P, kind of like that. So then your answer is going to be the vector that connects where you started from, which was up here, to where you ended up for Q, which is down at the bottom there. So this blue arrow that I've drawn, that is the sum of the vectors P plus Q. And oftentimes you'll find that people will give that new vector a new name. So it could be that P plus Q equals like R or something like that. And later on, we'll use letters that actually mean or represent a real quantity. Are there questions about that? I mean, it's I know it's kind of maybe, hopefully, it seems a bit straightforward, right? And so in this case, but it's important to understand these fundamentals because later on we'll be adding different quantities and we'll have what we call components to the vectors. So it is important. Now, and so in this case, it's important that you take P and then just connect them the right way. Otherwise, you end up with vectors that point not the right way. So anyway, that's kind of that example. So you can see the answer was A in this case. It gives you that vector that points down and to the left. So let's do another example where we consider the vector properties of the problem. So in this problem, we have Anna walks 90 miles east and then 50 miles north. What is her displacement from her starting point? Let me see. Okay, I'm just looking at the comments. So in this case, the idea is going to be that I should stop looking at these. All right. So in this case, the best thing to do is, so we're going to draw a picture of the problem. And so the first thing that they say is that she's going to walk 90 meters due east. So let's actually write down the information we have. So Anna walks 90 meters east. And then it says Anna walks 50 meters north. And we want to find out displacement from the starting point. So in that case, we'll start off with the first bit of information, which is 90 miles east. So I could just instinctively decide that I'm going to make an arrow that looks like that. But really, the very first step is to say, hey, well, we need to define our coordinate system. In this case, and the default is going to be in this class that up is usually going to be north, which means that everything else will fall into place, right? So east is going to be to the right on the screen. And so we'll label that vector with the size, which is 90 meters. And so in this case, the origin is going to be where we started off, right? So it's going to be the beginning of that 90-meter vector, okay? And then it says she's going to walk 50 meters north. So from that point where she just finished walking east, we'll say, okay, well, now she's got to go upward this distance, and that's going to be a distance of 50 meters. So the nice thing about this problem is that we've got a 90-degree angle between those two directions. And so that means we're going to have a nice right triangle when we're all done here. So in this case, the result or the answer for the displacement is going to be the arrow that connects the origin to where she ended up, okay? So this part right here, we can label the displacement. Displacement from origin, which is what we're looking for. And so in this case, we want to find displacement, so that means we need to find both magnitude and we need to find direction, okay? So for the first part related to magnitude, we can just use Pythagorean theorem. So in this case, since we want to find the displacement, we can call that our side C, right? So we're going to do our C squared equals 90 squared plus 50 squared. And that's going to give us, help us find the answer. So if you guys punch that into your calculator, what do we get for that magnitude? Let's try it out here. So 90 squared plus 50 squared, that's going to be 10,600, okay? But then we're going to have to take the square root of that value, right? So square root of 90 squared plus 50 squared is going to give us 102.96, okay? So from here, we get that C is equal to 102.96, which you can say is about 103. And if we wanted to really round out, we could say it's actually really close to 100. So there's more or less the size of this quantity, right? So 103 is more tempting as a number to write, but if we consider significant digits, 100 is the more appropriate one to use. So that's going to give us the magnitude. What about direction? So for direction, we're going to have to involve an angle of some sort. And so in this case, the You see it labeled on the picture. They've got a angle theta drawn right there. So the angle that we care about is down there. So let me label my cartoon here. So the angle that we're interested in is between that 90 and the, so basically it's the angle, you basically pick a reference point. In this case, I just chose the horizontal, the eastward direction as the reference point, and we're going to be going, slightly northward with respect to that eastward direction. And so in that case, if we're choosing that as the angle, and we want to use the information that's already there, then one of the best ways to do it is going to be to take the tangent of the angle equals, and so tangent is opposite, right, over adjacent. And so in this case, the tangent of that angle is going to be, well, the opposite to the angle is going to be 50 meters. And then the adjacent to that angle is going to be that 90 meter distance below it. So basically you have the tangent of theta equals 50 over 90, or equals 5 over 9. I mean, it's another way of doing it. So then the way to get the answer is going to be by taking the inverse tangent of the angle, or the angle is going to equal the inverse tangent, so tangent to the -1 of 50 over 90. So if we were to do that, what kind of answer would we get if somebody has a calculator, punch that in? So the first question is going to be, are you in degrees or in radians? For right now, I think it's best if we do it in degrees. So if you do tangents, I think on Google, they like to use A10 as the thing. So if you do it for 50 out of 90, you get this 0.507 radians. You can ask for it in degrees. And how do we do that? Yeah, so it should be 29 degrees. Okay, so thank you for that. This is what happens when nobody blurts out the answer. I just keep talking. So in this case, angle is going to equal to 29 degrees, or 0.507, something like that, radians. But in this case, that 29 degrees tells you the angle between the horizontal and your displacement vector. So in this case, the full answer is going to be basically 100 meters. And then this is the part where you have to get in the habit of writing it properly. So it's going to be 29 degrees north of east. Okay. So this of part basically means with respect to. So it's saying 29 degrees north with respect to east. So we're not quite east, but a little bit upward, okay? And so it's important that you write it this way, because if you write something like 29 degrees east of north, that's saying something very different. It's saying that you're pointing north and then you're kind of moving a little bit diagonally to the left or to the right in the eastward direction. That's different. So in this case, it's north of east, all right? Any questions? Is that kind of, so a lot of this is getting acquainted with the lingo if you haven't done this much before. So as we kind of go through, you can see they first did what we did, the Pythagorean theorem. So they also got that 103. And then you do the inverse tangent of 5 over 9. That gives you 29 degrees. And so finally, we get the answer, right? And it is important to look at the answer and see whether it makes sense or not, right? Because if you drew a triangle where the bottom was 50 and the vertical part was, I'm sorry, where the bottom part was 90 and the vertical part was 50, then you kind of know that you got to get a small angle, right? You're not going to get an angle that's more than 45 degrees. You're not going to get an 80-degree angle. If you get an answer that's like 120 or something, then you have to reevaluate and be like, okay, what is this actually telling me, and did I do it? So in this case, it makes sense. It's going to be kind of a shallow angle. If it had been 90 and 90, then that would be a nice isosceles triangle. It'd be 45, and so you expect to get an answer like that, you know? So it's good to stop and just check before you move on. So it turns out for velocity, we're going to do something very similar to represent velocity vectors. One of the things that the book does that does pretty well is the book likes to color code things. So for example, for displacement, it likes to use blue arrows, and I can't guarantee you that I'll do it, but I'll try. The book also likes to, when it comes to velocity, it likes to use green arrows. And you'll notice that as we go and find other vector quantities later on, we'll have different colors for other quantities. And that's just to kind of keep you guys kind of from getting confused, because you might have multiple types of arrows in one cartoon. But you can see in this example that how, you know, we have on part A, we have the displacement vectors. And so you can see that, you know, at each time increment, the displacement vector keeps getting longer and longer. That's because we're covering more space in the same time interval, which also means that if you plot the velocity, those arrows will be getting bigger because it means we're going faster. So that kind of makes sense. And this is just a, you know, that was a short example, easy example. We'll be doing the same kinds of vectors for two-dimensional motions. In this case, somebody threw a ball up. You can see that the beginning, you know, has a high velocity. As you're getting to the very top of the trajectory, the velocity vectors get smaller and smaller. And then it starts getting ready to go back down, and it starts to speed up again. But one thing that you should see here is that the fact that it's symmetric, right? The very first arrow looks same size as the very last arrow at the end of the trajectory. And on either side of the maxima, you get arrows that are the same size. And that's going to be true of all what we call projectile motion. This is motion in two directions when you just throw something, okay? The only exception is if there's like, you know, air resistance or there's wind, that can modify those vectors. But a lot of time we're going to be ignoring that in this class. And so for the most part, you can always assume when we're doing projectile motion, it's going to be symmetric motion. So if somebody asks you, well, what's the starting velocity, and you know it, well, you kind of automatically know the final velocity. You just have to make sure that it's pointing downward in the right way. But we'll do examples of that later. So where do we go from here? Well, so far we've this is a good time to kind of pause and for you guys to take a look at the structure of how the lecture slides are organized. Typically, when you start, when you look through the beginning of the slides, there's always going to be like a preview, kind of letting you know what's in the chapter, and if there's important concepts, it'll ask you to go and make sure you understand concepts. So for this chapter, you know, Pythagorean theorem, sine, cosine, all that stuff is important. And every chapter will remind you of things that you should already know by now. The ends of the chapters have really good summaries on the topics that were discussed. So if you're doing the homework and you kind of feel a little stuck and you don't know where to begin or what part of the lecture notes to look at, sometimes a summary is a good place to start. You can see it all condensed in a few slides and helps orient you a bit. And the reason I'm saying this is because I'm not going to be going in very much detail through those summary slides or through the beginning slides. It's something that I hope that you guys do kind of before class or when you study. It's good to look at the summary slides as well to make sure you didn't leave out any important concepts. And so that's kind of, and so in the new lecture notes, they're arranged the same way. But actually, before we move on to this example, that's the other part that I wanted to, before I start having technical difficulties, there is a mini assignment that I'd like you guys to do. So if you look at the new slides, chapter 2, slide 22 has a link to a video, to a chapter 2 video. So just please watch it before class next time. Like I said, it's just a 4-minute video. It gives you a little bit of summary of what the chapter is about, and the guy giving the video is, you'll learn to like him. He's this cool long-haired hippie. I forget which one that is, which of the authors. I think it's the last author in the of the 3. So let's go ahead and work on this example here. Just trying to, okay. So in this example, it's called a goose gets its bearings. And here's an idea. Hold on, let me just try something real quick. Because I'm wondering if I can use the zoom tool instead. Maybe not. Oh well. Okay, so in this example, it says here, we have, so the figure below shows a path of a Canada goose that flew in a straight line for some time before making a corrective right-angle turn. 1 hour after beginning, the goose made a rest stop at a lake due east of its original position. And then we're gonna have to answer some questions that are in the next slide about this. So first thing is, let's go ahead and draw a picture of this situation. So start of the journey is up here at the top. And this goose traveled a distance of 21 miles. And then it says at some point, it just says sometime later, it took corrective right angle turn. So it's corrective 90-degree turn. So this is kind of like the goose going, oh crap, missed the lake. If you could get inside the mind of the goose, right? Perhaps that'd be what he's thinking. So he decides, oh, well, I gotta turn back, gotta go this way now. And so now, so we got this nice 90-degree angle, and we've got so the finishing spot is the end of trip right here, and it's a lake. So, and they also label a few other things for us here. They tell us that after he made that 90-degree turn, he had to fly another 28 miles to get to that lake. So, and it says 1 hour after beginning, it finally gets to the lake. So the total trip took 1 hour. All right, so that's kind of, I think, all the information that we need for this problem. And once again, we're gonna have to define our north, south, east, west. So as before, we'll make the north point upward, okay? So then in this problem, they wanna know, in part A, how much extra distance did the goose travel due to the initial error in flight direction? So how much farther did it fly than if it had simply flown directly to its final position on the lake? So in other words, what they're saying here is, in this problem, I mean, if it hadn't messed up, right, the goose would have just gone from the start to the end and everything would have been fine. So this part here, this is like the ideal path, right? It's basically, instead of having gone down, you could have just gone straight from the start to the lake, and that would have been best. So for part A, really what they're asking is, how much extra distance did it go? And so the idea here is going to be to take the actual path. Not B, rho. So actual path minus ideal path is going to give you the extra amount that he traveled, okay? And so the first part is, okay, well, what is the total path? Well, we got 21 miles plus 28 miles. So down here, total path is 21 plus 28, and what does that give us? 49 miles, okay? So that's one part that we need. The next part is the ideal path, right? And so for the ideal path, how do we solve that? Well, we have, if you remember, a nice 90-degree turn here, right? Yeah, so we use Pythagorean theorem. So for the ideal path, we use Pythagorean theorem. And so in that case, let's just call the ideal path equal to the length c. So in that case, you're going to have c squared equals 21 squared plus 28 squared. So you're going to take that and then take the square root of it to get c, and that will give us the answer. So I can take that. And if somebody already did it, you could just blur out the answer. Say it loud. 35? All right, so we got an answer of 35 for the distance. So C is equal to 35. So 35 miles was the ideal path. So then that means the extra, if you solve for this, is going to be the 49 minus the 35. And that's equal to 14 miles extra, okay? And so that's the first part of this problem where they ask, how much farther did they fly? Well, he went an extra 14 miles that he didn't have to fly, okay? Next question is going to be, are there any questions about that, by the way? Okay. So the next part is, well, what's the flight speed? Well, flight speed is just going to be the total distance over time. And so in this case, we know the time, it's, at the very top, it says the total trip took 1 hour. So the flight speed is just going to be a total distance of 49 miles divided by an hour. So 49 miles an hour is the speed of this goose. And so in this case, if you convert 49 miles an hour to kilometers per hour, it's about 80. And once again, it's also a good time to kind of stop and think, okay, is that number reasonable or not? And really what I'm asking you to do in this case is to think about, does that number seem okay? So 49 miles an hour, okay, that's about as fast as a vehicle drives on some roads, highways. You should be worried if your answer is like 2 miles an hour, right? Because 2 miles an hour, that's about as fast as a person can walk. And we know birds go faster than you can walk, so you would do a double check in that case, make sure you did it right. You should also be worried if the answer is like 300 miles an hour, right? Because that's how fast airplanes fly, not a goose. If you had a 300-mile-an-hour goose, I mean, that'd be impressive, or he's doing some kind of trickery to fool you. So, and the trickery could be that it's really windy, okay? Maybe it's a goose in a hurricane, you never know. But those numbers are reasonable, and then we get to kind of move on. So in this case, we mainly use the fact that these are vector quantities, and the main thing is to get in the habit of knowing how to connect all the arrows together. So in this case, we did the displacement vector of the 21 miles, and then we did tip to tail to attach the 28-mile vector to that. And then the answer, the displacement, was the connection between the starting point and the end point, right? And so there will be a lot of problems kind of like that for chapter 1, the homework on assignment. So are there any questions about that stuff so far? So some of the concepts that we covered today or from last lecture was motion diagrams. We understood what those dots mean, and we went from there to being able to write down vector quantities and represent them using arrows. We went over tip-to-tail method on how to connect them. And we also talked about how velocity vectors, you work with them the same way. You connect the vectors in a similar fashion. The kinds of questions that we'll ask when we're talking about velocity might be slightly different questions, but you still approach it the same way. If you need to add two vectors. So for example, one particular problem that we'll do later as well is you might have a velocity vector where maybe, let's say you're flying north at, say you're on a little two-passenger plane, maybe you're going 100 miles an hour, straight north. Maybe we're pointing to Albuquerque. But as you're going north, maybe it's really windy. Maybe usually the wind goes west to east around here, right? Maybe it's like a 50-mile-an-hour wind. Well, now you've got two velocity vectors, right? You've got your velocity vector of 100 miles an hour north plus 50 miles an hour east. Well, that's going to give you a net velocity that's not going to be pointing north. It'll be pointing a little bit off to the side, a bit eastward. So you would do the same thing. You take your two vectors, use Pythagorean theorem to find the resulting vector. So in this case, since we're dealing with 90 and 50, the answer would be slightly larger because the hypotenuse part. So you'd have that velocity vector quantity. And then to find out the angle that it's making by the end of the trip, you will have moved over sideways a little bit. And that angle, you calculate it using the same tangent function we did earlier. And so you might find out, well, actually it's, I don't know, it might be something like 120 miles and maybe 20 degrees east of north. So instead of Albuquerque, you might end up in the neighboring town. What's a neighboring town to Albuquerque? Anybody know? Anybody driven up there? You guys should take that trip one day, like Route 66, all that stuff. But anyways, there's I think Santa Rosa is like another little town that's nearby. So who knows? You might end up in the wrong airport, right? If you don't pay attention to wind speed and that kind of stuff. So if there's any amateur people that fly, I mean, you can. I'm sure you learn these things, right? Well, nowadays there's tools that tell you where you are, but that wasn't always the case for me. So I'm rambling now, but think about things like Vikings, right? Did you guys know Vikings were the first people in the Americas instead of like Christopher Columbus and stuff? They showed up like hundreds of years before, like, paid European settlers, sponsored by like, monarchs. But they kind of got here by accident as well. And it's just because, I mean, yeah, they could see, they use the stars for guidance, but it was also incredibly windy. And so they got lucky that they found some land. Right? But yeah, I mean, sometimes one thing that is enjoyable, I think, especially nowadays, and I really am rambling now, but so if you guys online want to log out, I'm not going to get mad. But really, if you think about this instance now being in the we have this pandemic, right? We're all in quarantine. We're connecting to each other using technology, but it's important that you not rely on technology too much, because the moment it's gone, like, what are you left with? You have to make sure you can get around and survive, right? And having that little bit of knowledge of how the physical world around you works is useful. If you know it's going to be windy and worst case scenario, right? Civilization collapses, you have to go hunt rabbits or something. Well, guess what? You're going to have to point that arrow the right direction if you want to have a meal that day. So you're going to do some quick math in your head to point things the right way. If you play sports, you guys know, if you're outside playing basketball and it's a windy day, you got to correct for that. And we kind of do it instinctually, but there's mathematics that explains it exactly. But going back to the point of technology, right? I mean, I think about this a lot because all it takes is for communications to go down, right? And there's scientists you probably always see news feeds about, an asteroid came this close to the Earth, or is going to come really close to us in a few weeks. In principle, we don't have a way to stop that, right? And so we happen to be unlucky and maybe not even have something hit the Earth, right? But it knocks out a few satellites. All of a sudden, your Spectrum and your T-Mobile or any source of internet goes away. And so it's like, all right, well, now what? I mean, right now, the way things are, then you just take the day off, man. Go to the park and have fun. But at the same time, I am trying to prepare things. That's why I give you guys slides. So I say, hey, You guys got your stuff, study it. If something happens, like my professor can operate his damn stupid pen, you guys have tools to try to figure things out, and you can still get in touch with me, ask me questions. So today's a good example of that. I mean, I wanted to present it a little bit better, but we move on. So that's all there is for chapter 1. We're going to start chapter 2 next time. It's going to be motion in 2 dimensions, and we're really going to get into the vectors there. We're going to be breaking them up. We're going to realize that vectors have an x and a y components, and we're going to go through the math on how to separate those out to solve slightly more complicated problems coming up. All right. So just to recap, just watch out for a message from me on registering for the homework, or for the mastering physics. And if you have questions about that, just let me know. You can ask me directly or send me a message, whatever. Okay. All right, guys. So that's it. We'll see. Well, we'll see you guys online Wednesday, and everybody else, whatever. See you Wednesday. Take care.
I have a question, sir.
Yes.
So you said that you should be posting the Pearson either later today or sometime this week. Is there any homework due?
So the instructions will be given out today, and then the homework that I assign, I will assign it either today or tomorrow, and that's going to be due on Wednesday the 9th.
Oh, okay, thank you.
I have a question.
Yep.
Can you show us while you're screen sharing, or can you show me where the slides are for chapters 1 through 11? Because I cannot find them on Blackboard.
Oh, okay.
Please.
Sure. You can see my screen right now, right?
Yes.
Okay. Yeah, so let's do that. So if you go here, so your class is 14,700, it's right here. And it's a good thing you're asking me to check, because there is a chance that maybe I did something wrong. Yeah, so if you click on the lecture slides thing, this thing opens up. Everything you see at the bottom, it says lecture notes, college physics, 4th edition, night. Everything below it is all the PowerPoint slides. So I recommend you download all of them. But I guess for the first thing is to let me know if you can see this or not on your account. But you should be able to. And then you just click and download. I think if you click on the main one, you can maybe download everything. Oh, maybe not. Okay.
But I think the order for those sets of notes were different from the first sets of notes.
Can you say it again?
So I have another set of slides with the first picture, with the first picture being the college physics, but it's like a red cover. And then those slides are with a blue cover, and the order are different.
Right. So what we went over class today was the ones in the first tab, and those do have the red cover. Starting Wednesday, we'll do chapter 2, and I'll move on to the new slides that have the blue cover on them.
Awesome. Thank you so much.
Okay, I found them.
Sure.
Thank you.
Good. Other questions? All right, guys. In that case, I'll talk to you later.
Have a good day. Thank you.
Thank you. You too. Bye.